Hello and welcome to UFLYUAS tutorials. In this beginner-friendly tutorial, I'll guide you step-by-step on how to create free 2D maps using waypoints. You'll learn how to generate an ortho mosaic, a digital surface model, DSM, and a digital terrain model, DTM, including how to classify your point cloud to accurately produce both models. I'll also show you how to use Google Earth Pro to create stunning 2D map tours, and how to generate professional reports using RealityScan software and the DJI Mini 5 Pro, all without spending a single dollar on subscriptions or expensive software. Although I'll be demonstrating with the DJI Mini 5 Pro, this tutorial is designed for any skill level and can be followed using any drone. All images are available for download in the video description so you can easily follow along from start to finish. Let's get started. Since the client has requested a 2D map of this baseball field, we'll start by planning a waypoint mission to capture all the images required for mapping. In this segment, I'll show you just how simple and efficient it is to set up a waypoint mission, without the need for any expensive apps or paid subscriptions. Power on your controller, and please note that you don't need to turn on your drone for this step. Simply swipe down from the top of the controller screen to access the quick menu interface. Next, tap the settings icon, then select Network and Internet. From there, choose your preferred Wi-Fi network. In my case, it's called Personal Hotspot. Enter your Wi-Fi password, then tap Connect. Once your controller is connected to the internet, you'll be ready to move on to the next step. In the DJI Fly app interface, tap Connect to Aircraft. In the Select Aircraft Model window, you'll notice that tapping on DJI Mini 5 Pro will cause the controller to start searching for the drone. However, since we're only planning a mission and don't need to connect to the aircraft right now, instead click on Camera View. This will give us access to the map interface and the waypoint mission tools, allowing us to start planning our flight path and setting up all the waypoints needed for the 2D map project. Click on your map display to expand it, then change the map layer to Satellite View. This provides a more detailed and realistic view of the area, making it easier to identify landmarks, field boundaries, and other important features when planning your waypoint mission. Now, zoom out on the map to get a full view of the entire area you'll be mapping. This wider perspective will help you clearly define the boundaries of the area and ensure that your waypoint mission covers the entire site with proper overlap and coverage for accurate 2D map reconstruction. Whenever you're mapping an area, it's important to start your flight path outside the actual boundaries of the site. Doing so ensures you capture enough image data along the edges, which is critical for producing a clean and complete map. If you start your first flight line directly on the boundary, you risk finishing the mission and later discovering gaps or missing data near the edges. By extending your mission slightly beyond the area of interest, you'll guarantee full coverage and better stitching results during map processing. Now let's zoom in on the map to locate the exact area where we'll place our first waypoint. Next, click on the waypoint icon. This will open the waypoint mission menu, giving you access to all the tools needed to start creating and customizing your mapping route. Once you've confirmed the exact area where you'd like to place your first waypoint, simply tap on the map, and it will automatically drop your first waypoint at that location. This marks the starting point of your mapping mission, from which you'll continue adding additional waypoints to define the full flight path. Now, I'll continue dropping additional waypoints along the path to complete the first flight line. Make sure each waypoint is evenly spaced and follows the general direction of your mapping area. This will help maintain consistent overlap between images and ensure accurate data capture for your final 2D map. Remember to always start outside the boundaries of the area you're mapping. Now that I'm approaching the edge of the site, it's very important to place one waypoint directly on the boundary line and then add another waypoint slightly beyond it. This step is crucial because the waypoint mission automatically creates a turning loop at each end when the drone transitions to the next flight line. By extending your waypoint slightly beyond the boundary, you'll ensure that the turning loop doesn't interfere with your next flight line, which needs to run parallel to the previous one. This approach helps maintain perfectly aligned passes and consistent spacing between flight lines, resulting in clean, professional mapping patterns and accurate image overlap. The key to achieving the best results in a 2D mapping waypoint mission is to create small loops at each end of your flight path using 2 waypoints per loop. This technique allows the drone to make smooth, consistent turns between each flight line, reducing sharp movements and ensuring precise alignment and overlap across all image captures. By incorporating these loops, you'll produce cleaner, more accurate 2D maps with minimal stitching errors. Now we'll complete our 2D waypoint mission by adding loops at each end of the flight path, following the same rules and spacing as before. These end loops will ensure the drone maintains smooth transitions between each line, keeping all flight paths parallel and evenly spaced for consistent image overlap and optimal mapping accuracy. Continue adding waypoints across the entire site, following the same spacing and looping rules until you've completely covered the entire mapping area. Make sure each line remains parallel and evenly distributed, with loops at both ends, to achieve consistent image overlap and full ground coverage for your 2D mapping mission. You can now zoom out on the map to review your waypoint layout. Take a moment to adjust any waypoints that may be slightly off, so your flight lines appear as straight and evenly spaced as possible. Your lines don't need to be perfectly straight, but they should be close enough to maintain consistent image overlap throughout the mapping area. This ensures smooth stitching and accurate results when processing your 2D map later on. The most important thing to remember is to extend your flight path beyond the site boundaries and create 2 waypoints at each loop. You should also have 2 waypoints positioned right at the edge of the area you're mapping. This setup gives you greater flexibility when adjusting and straightening your lines, helping you keep all flight paths tight, parallel, and evenly spaced for a clean and precise 2D mapping layout. Now is a great time to save your waypoint mission. Simply click on the small notepad icon to open the Save menu. This will store your current mission setup, ensuring that all your waypoints, loops, and mapping parameters are safely saved and can be easily reloaded later if needed. Click Save or choose Save As if you'd like to assign a specific name to your mission. For this tutorial, I'll simply click Save using the default name convention provided by DJI. Once saved, I'll tap the back arrow to return to the waypoint mission interface and continue setting up the rest of the mission parameters. Now, I want to adjust the global speed by clicking the 3 dots in the waypoint menu. This global speed will tell the drone to fly the entire waypoint mission at your desired speed. For this mapping project, I'll set the flight speed to approximately 6 miles per hour, which helps ensure excellent image overlap for accurate stitching and high-quality results. I'll leave all other settings at their default values, as they're well suited for this type of 2D mapping mission. Simply click the back arrow to return to your waypoint list. Locate your first waypoint, labeled Waypoint 1. Here, we'll adjust several key parameters to optimize your mapping mission. Let's begin by adjusting the camera action setting. You'll notice there are 3 options available: None, Take a Photo, and Start Recording. For this particular mapping project, I'll set it to None. By setting it to None, it allows us to maintain full control over when and how images are captured during the mapping process. Next, let's adjust the altitude. I'll set it to 200 feet, which provides excellent image overlap and high-quality detail for the 2D orthophoto map that the client has requested. This altitude strikes a good balance between coverage area and image resolution, ensuring the final map is both sharp and accurate. It also provides a safe buffer from any potential obstacles, such as tall trees around the field. Next, let's verify that Waypoint 1 is using the global speed setting we configured earlier. This ensures the drone maintains a consistent flight speed, in this case 6 miles per hour throughout the entire mission, which is essential for uniform image overlap and smooth mapping results. The next setting is the Follow Course heading. You'll always want your drone to follow the course direction, especially during mapping missions. This ensures that the drone's camera remains aligned with the flight path, maintaining consistent orientation and overlap between each image. It also helps produce smoother flight lines and more accurate stitching when processing your 2D map. The next setting is the gimbal tilt. Since we're creating a 2D map, we'll set the gimbal to -90 degrees, which means the camera will be pointing straight down. This nadir angle is essential for mapping because it captures imagery directly over the surface, minimizing distortion and ensuring accurate stitching when generating the orthophoto. You can leave the remaining settings at their default values. Now that we've completed all the necessary settings, take a moment to double-check everything. Make sure your altitude, gimbal tilt, flight speed, and course direction are all correct. Once you've confirmed that everything looks good, click Apply to All. This will apply the same settings to every waypoint in your mission, ensuring consistent flight parameters and image quality across the entire mapping area. Simply click OK, and you'll notice that all your waypoints now share the same settings throughout the entire mission. This ensures that every segment of your flight, each altitude, speed, gimbal angle, and heading, is perfectly consistent, resulting in a smooth and uniform 2D mapping operation. Now that we're satisfied with all our settings, I'll click the back arrow and save the entire mission once more to ensure that all the recent changes are securely saved. This step guarantees that every adjustment, from altitude and gimbal tilt to global speed and course direction, is properly stored and ready for flight execution. Now that all the settings are configured and saved, let's power on the drone and prepare for the actual flight. Great. The drone is now powered on and connected, and we are in our waypoint mission, which means we're ready to begin the mission. Go ahead and click Go on the waypoint mission. This will initiate the automated flight, and your drone will begin following the pre-planned route to capture all the necessary images for your 2D map. Click Continue on the safety warning message. The drone will automatically take off and fly to the first waypoint to begin the mission. From there, it will continue along the predefined flight path, following each waypoint and maintaining the settings you configured for altitude, speed, and gimbal tilt to ensure precise and consistent image capture. Once the drone reaches the first waypoint, I'll pause the mission to configure the camera settings. This allows me to fine-tune parameters such as shutter speed, ISO, white balance, and exposure before the mapping begins. Setting these manually ensures consistent image quality across all photos captured during the mission. Click on your drone's camera view to open the camera interface. Now that we're in the camera view, I'll manually tilt the gimbal to -90 degrees, pointing the camera straight down toward the ground. With the gimbal in this position, I'll adjust all my camera settings, including shutter speed, ISO, and exposure, to achieve the correct brightness and color balance for the mapping conditions. Setting these values while the camera is facing straight down ensures accurate exposure readings that match the actual lighting of the mapping area. Next, switch the camera from Auto mode to Pro mode. Let's start with the white balance. Click on your white balance value to open the white balance menu. I'll first set it to Auto, to let the camera detect the correct color temperature for the current lighting conditions. Once it looks accurate, I'll turn Auto off to lock the white balance in place. This step prevents the camera from shifting colors between photos, ensuring consistent tones and accurate color reproduction across your entire 2D map. Next, make sure your photo format is set to JPEG. Set your aspect ratio to 4/3, which utilizes the full sensor area of the camera for maximum image quality. Then, adjust your photo resolution to 50 megapixels to capture the highest level of detail possible for your 2D map. Finally, ensure that all photos are being stored directly to the memory card, so you have full access to the image files later during processing. Next, click on the camera shutter icon to open the ISO and shutter speed menu. This is where you'll fine-tune your exposure settings to achieve a properly balanced image. Adjusting the ISO and shutter speed manually gives you consistent brightness and clarity across all captured photos, which is essential for accurate stitching in your final 2D map. Set both ISO and shutter speed to Auto first to allow the camera to automatically determine the correct exposure for the current lighting conditions. Once you're satisfied with the exposure level, turn Auto off for both settings. The individual values may fluctuate slightly, but the key is to ensure the exposure compensation, EV value, stays at 0 or as close to 0 as possible. This will lock your ISO and shutter speed in place, guaranteeing consistent exposure across every photo captured during the Waypoint mission, essential for maintaining even brightness, accurate color, and high-quality stitching in your final 2D map. If you recall from earlier, when we were configuring the Waypoint camera settings, we intentionally set the camera action to none. The reason for this is that, as you can see here, I've set my camera to time shot mode with 5-second intervals. This setup ensures that photos are captured automatically during the flight without needing to assign a photo action to each waypoint. If you're not sure how to set this up, I'll walk you through the steps so you can easily configure the timed shot interval yourself. Let's go through how to set up timed shot mode at 5-second intervals. click on the video icon on your screen and switch from video mode to photo mode. Then, select timed shot from the available photo options. Make sure the interval is set to 5 seconds to achieve consistent image capture and proper overlap throughout your mapping flight. Once this is set, you're ready to resume the Waypoint mission and start capturing all your mapping images automatically. Okay, let's go back to our Waypoint mission and double-check all our settings before starting. My camera action is set to none and applied to all is already set. I'll confirm that my altitude is correct and click Apply to All, hit OK to confirm the changes. I will do the same for my global speed, follow course heading, and gimbal tilt. This ensures every single waypoint in the mission is perfectly synchronized with identical settings for consistent and accurate data capture. Let's click the back arrow, then click the 5-second interval shot. Once that's set, switch to your map view, tap Next, and then click Go. The drone will now begin flying the waypoint mission you created, following all the settings and parameters you've configured for a smooth and consistent 2D mapping flight. Be patient and allow the drone to fully complete the mission. And the best part is, you didn't need to purchase any apps, pay for subscriptions, or upload any KMZ or KML files to your drone using a computer. Everything was done directly through the standard DJI application. Simple, efficient, and completely free. Once it finishes capturing all the images, it will automatically return to the home point. After the drone lands safely, you're ready to move on to your computer to begin processing the images and creating your 2D map. These tutorials are designed for beginner drone pilots who may not have the budget to purchase expensive apps or subscriptions. My goal is to help you achieve the same professional quality results without spending any money or breaking the bank. Now that we've captured all the images, let's go ahead and transfer them to the computer. Remove the SD card from your DJI Mini 5 Pro, then insert it into your computer's SD card slot or use an external card reader. This will allow you to access and transfer your captured images directly to your computer for processing. Create a new folder on your desktop and transfer all your images into that single folder. Keeping all your photos in one centralized location makes it easier for RealityScan to locate and process the files efficiently, without needing to search through multiple directories. We captured a total of 203 photos during the Waypoint mission, flying at an altitude of 200 feet and a speed of 6 miles per hour. This combination of flight height and speed provided excellent image overlap and high-quality detail, ensuring the dataset is ideal for generating an accurate and seamless 2D orthophoto map. All the images used in this tutorial will be available for download via the link in the video description, so you can easily follow along with this beginner-friendly 2D map photogrammetry tutorial. In my previous 3D photogrammetry tutorial, also linked in the description, we discussed Epic Games, the company that owns the RealityScan software we'll be using to create our 2D map. To get started, you'll need to download and install the Epic Games launcher and create a free account to access RealityScan, which is completely free to use. You can also click on Unreal Engine from the left side menu within the Epic Games launcher, then select RealityScan from the top menu to access the application. From there, you can verify that you're using the latest version of RealityScan and ensure that automatic updates are enabled, so the software stays current with the newest features and performance improvements. Begin by opening RealityScan. When you launch the app for the first time, you'll be greeted by the welcome screen. Here, you'll find a variety of tutorials, guides, and helpful resources designed to help you get familiar with the software. This initial view is known as Single View Mode, where you can preview your workspace and access learning materials before starting your first project. RealityScan offers several view modes that you can experiment with to find the layout that best fits your workflow. Personally, I prefer using the 1+2 view mode, as it provides a balanced and efficient workspace, allowing you to visualize both your model and the image alignment process side by side for better control and understanding. The first tab in RealityScan is called Workflow. This is where you'll import your images into the software and begin setting up your 3D reconstruction process. The Workflow tab serves as the starting point for every project, guiding you through the essential steps from image loading to model creation. Let's go ahead and load our images into RealityScan. You'll have two options: Input or Folder. Since all my images are stored in a single folder, I'll select the folder option. This method keeps the import process simple and ensures that all the photos are added at once for processing. Go to the folder where you saved all the images you captured during the Waypoint mission. Once you've located it, click Select Folder to begin loading all the images into RealityScan. The software will automatically detect and organize your photos, preparing them for processing into your 2D map. Next, click Alignment and select Align Images. This step allows RealityScan to analyze and align all the photos based on their overlapping features. Once completed, the software will generate a sparse point cloud, which represents the basic 3D structure of your mapping area using a minimal number of points. This step may take some time to complete, depending on the number of images you have to align and the processing power of your computer. Great! Now that all the images are aligned and we have a sparse point cloud, let's save our project. Click on the RealityScan icon, select Save As, give your project a clear, descriptive name, and then click Save. This will ensure that all your progress and alignment data are securely stored before moving on to the next steps. Now that our project is saved, let's learn how to navigate the 3D point cloud using your mouse. To rotate the 3D point cloud, click and hold the right mouse button while moving your mouse in any direction. This allows you to freely explore the model from different angles and perspectives. Press and hold your left mouse button to move the 3D point cloud left, right, up, or down. This lets you pan across the model and examine different areas without changing the viewing angle. Use your mouse scroll wheel to zoom in or out on the 3D point cloud. This allows you to get a closer look at details or zoom out for a full view of your mapping area. In this 3D view, you can see the Waypoint mission layout and all the photos captured during the flight. You'll also notice the 3D point cloud of the baseball field, which represents the spatial structure of the area. Surrounding the point cloud is the bounding box, and in the center, you'll find the rotate gizmo, which allows you to manipulate and rotate the binding box precisely within the workspace. Let's rotate the 3D point cloud to achieve a top-down view. This perspective provides a much clearer view, making it easier to adjust the bounding box accurately around the area we want RealityScan to process. Let's start by turning off all the camera icons. You do this by going to the Scene 3D, click View, and uncheck the box labeled Enable. This will hide all the camera markers from the workspace, giving us a cleaner view of the point cloud and making it easier to make adjustments. Let's rotate the bounding box by grabbing the gizmo in the center. Then, adjust the bounding box using the control points so that it encloses only the area we want to process, leaving out any unnecessary points that don't need to be included. This helps focus the processing only on the region we selected with the binding box. Use your mouse scroll wheel to zoom in and carefully verify that the bounding box is positioned correctly. Make any final adjustments to ensure it fully encompasses the area you want to process while excluding unnecessary points. This step ensures accurate and efficient processing for your 2D map. Once you're satisfied with your bounding box adjustments, click on Mesh Model and select Preview. This will generate a preview of the selected region, allowing you to see how the mesh will look before final processing. It's a helpful step to verify that only the desired area is included and everything appears correctly. Looking at the mesh, I can tell that the overlap created during the Waypoint mission was excellent, as there are no visible holes or gaps in the mesh. This confirms that the flight path and image overlap were set up correctly, resulting in complete coverage and high-quality data for the 2D map. Go ahead and click View under the Scene 3D menu, then select Suite Mode. This will give you a clearer visualization of your 2D map, displaying the mesh with more natural lighting and surface details, making it easier to assess texture quality and overall map accuracy. If you click on your 2D model, it will reactivate the bounding box, allowing you to make additional adjustments if needed. This is helpful for refining the exact area you want to process or trimming out any remaining sections that aren't part of your final map. Once you're satisfied with your final adjustments, click on Mesh Model again. Since we're creating a 2D map and not a full 3D model, we don't need the highest level of detail. This time, select Normal Detail. It's faster to process and provides more than enough quality for generating an accurate 2D orthomosaic. The normal detail process may take some time, depending on the number of images you're processing and the overall performance of your computer. It's best to step away and let Reality Capture reconstruct your 2D model without interruption. Once the process is complete, you'll have a clean, well-detailed mesh ready for generating your final 2D map. Now that we have our mesh set to normal detail, let's add texture to bring out the surface details and color of the 2D map. Click on Settings next to Texture and verify that the maximal texture resolution is set to 8192 by 8192. Next, check that your style is set to Maximal Texture Count. This ensures your final 2D map will have sharp, accurate colors and high visual quality. Now that we're satisfied with our settings, let's click Texture. This process may take some time, as RealityScan is now applying the texture to your normal detail mesh, adding realistic color and surface detail to your 2D model. Now that we have both a cleaned and textured model, let's organize them properly by renaming each one in the 1Ds panel. To do this, make sure you expand Component 0 and simply click on Model 1, then rename it to something that works best for your workflow. In my case, I'll rename mine to Original. Giving your models clear names helps keep your project organized, especially when working with multiple versions or stages of classification and cleanup. I'll also rename Model 2 to Cleaned, so I can easily recognize that this is my cleaned and textured 2D model. This is looking incredible. The level of detail and texture on this 2D model is outstanding. There are no visible gaps or holes, and the overall surface looks clean and consistent. The 2D model turned out amazing, showing just how effective proper flight planning and overlap can be. This is just to show that with the right settings and a little patience, you can achieve both 2D and 3D models right inside RealityScan. You don't need expensive software or costly subscriptions, just technique, consistency, and creativity that gives you excellent results. The level of detail you can achieve with RealityScan is truly impressive. Every texture, every shadow, and even the smallest surface variations are captured with stunning accuracy, allowing you to create 2D and 3D models that look professionally made. The key lies in precision, using the right angles, consistent lighting, and enough image overlap to let RealityScan reconstruct every detail. With proper technique and patience, your results can easily rival what's produced by expensive professional software, proving that mastery of your workflow matters far more than the price of your tools. Now, let's take it a step further. I'll show you just how easy it is to classify your point cloud for man-made objects using RealityScan's AI Classify feature. With just a few clicks, you can automatically detect and separate elements like buildings, cars, and other structures, saving hours of manual work and bringing your model closer to a professional, production-ready result. Even though this step wasn't requested by the client, I want to quickly go over it so you can learn how to perform classification and how to create either a digital terrain model or a digital surface model. This section is simply to help you understand where the settings are located and how you can use them to generate accurate ground and surface data whenever needed in a professional setting. Click on Tools under the Scene 3D tab, then select AI Classify. This will open the AI Classify settings panel on the left side. Look for Type of Classification and choose Mixed Landscapes and Construction Sites. Once selected, simply click Classify Model, and RealityScan will automatically begin identifying and labeling man-made objects within your point cloud. You might be wondering, why even bother doing a classification? The main reason is accuracy and control. Classification allows you to separate what's natural from what's artificial, like removing trees, vehicles, or buildings, so you can focus only on the true ground surface. This makes it possible to create precise digital terrain models or clean 3D reconstructions without unwanted clutter. In short, classification is the key to transforming a raw point cloud into a clean, professional dataset ready for mapping, modeling, or analysis. A digital surface model, DSM, represents everything that's visible from above, including the ground and all the objects on it, such as buildings, trees, vehicles, and other man-made structures. It captures the true surface of the area as it appears from the air. A digital terrain model, DTM, on the other hand, represents only the bare ground surface with all those objects removed. It's used to analyze the actual topography or elevation of the land itself. Now that you have a better understanding of the difference between a digital terrain model and a digital surface model, Let's take a look at how well the RealityScan AI Classify feature performed. You'll see how accurately it was able to separate man-made structures from the natural terrain, giving you a clear visual of just how powerful this automated classification process can be. In your left panel, you can now expand your cleaned model, then open model classes, and further expand classification. You'll notice that the AI automatically created 4 different classification groups: ignored, none, ground, and artificial objects. These categories help organize your point cloud, and as you can see in the 3D view, the artificial objects such as cars, bleachers, and structures are clearly highlighted, separated from the ground layer for easier analysis and refinement. Let's remove all the artificial objects from the ground classification so they don't get included as part of the terrain. To do this, go to the 1Ds panel and select Artificial Objects. At the bottom, you'll see the menu options for this class. Simply click Select. Under Scene 3D, click Tools, and then choose Filter Selection. This process will remove all artificial objects from the ground dataset, leaving you with a much cleaner and more accurate terrain surface for your digital terrain model. Now that the filter selection has completed and all artificial objects have been removed, you'll notice that RealityScan automatically created a new model in your 1DS panel named Model 1. Since we previously renamed our models to Original and Cleaned, to stay organized, it chose that naming convention. Let's go ahead and select Model 1. This is the newly generated filtered model. You'll notice that the point cloud now has several holes where the artificial objects used to be. These holes represent all the artificial objects that were removed from the scene. To fill these holes, simply click Fill Holes under Scene 3D, Tools, Close Holes. The Close Holes menu will now appear on the left panel. You can simply leave all the settings at their default values, then click Close Holes. RealityScan will automatically process the surface and fill in all the gaps created when we removed the artificial objects, resulting in a smooth, continuous terrain model. Now, if you look at your 1DS left panel, you'll notice a new model has been created, Model 2. This is your new digital terrain model, the version with all the holes closed and a smooth, continuous terrain surface. Meanwhile, Model 1 is the previous version that still contained the holes from the filtering process. You can now take a moment to rename these models according to whatever naming convention or workflow works best for you. Keeping your models properly labeled will make it much easier to manage your project as you move through different stages. Our next step will be to generate the Ortho 2D map, also known as an ortho projection, which will give us a detailed top-down view of the entire area. Perfect for analysis, visualization, or mapping applications. To do this, go to the Workflow tab, select your cleaned model, and click Ortho Projection. This will open the Ortho Projection tool on the 1DS left panel. Under Type, make sure it's set to Top. This will give you a nice top-down view of your 2D ortho photo. Next, look for Rendering Method and choose Image Mosaicing Aerial. Next, we want to set the ortho pixel size if you click Estimate. RealityScan will automatically estimate your ortho pixel size, but in this example, I'll manually set it to 0.05 and press Enter. Next, ensure that Generate DTM is switched to On, and confirm it's using the DTM from Classification 0 we created earlier. Once you're satisfied with all your settings, click Render. If you see an experimental feature warning, simply click Close, and RealityScan will begin generating your 2D ortho projection map. Great! Now that we've generated our 2D ortho projection map, you'll notice in the 1DS left panel, a new entry labeled Ortho Projection 1 is present. Select it, and next, under Ortho 2D tab, click View, and select DSM. As we mentioned earlier, a digital surface model represents everything that's visible from above, including the ground, buildings, trees, vehicles, and other man-made structures. It essentially captures the true surface of the area as seen from the air, making it perfect for visualizing elevation differences and above-ground features in your scene. Next, select DTM, which stands for Digital Terrain Model. This view displays only the ground surface, excluding all artificial structures like buildings, vehicles, or trees. It represents the bare earth elevation of your project area, making it ideal for accurate topographic analysis and mapping. You can also activate slope shading on your digital terrain model to better visualize elevation changes and gradients across the surface. This color-coded shading helps highlight steep areas, flat zones, and subtle terrain variations, making it easier to interpret elevation data and understand the topography of your project site. When you select Mosaicising, RealityScan will display your model as a series of tiles that make up the ortho image. Each tile represents a portion of the overall mosaic. If you click on any of these tiles, it will highlight and show the exact location of that image section on your 2D map, allowing you to easily identify which photos contributed to that part of the ortho projection. In more advanced workflows, you can even disable or replace certain tiles to improve visual consistency before baking the final ortho projection. In short, Mosaicising gives you precise control over the visual quality and accuracy of your final 2D map. Next, click View again under the Ortho 2D panel and select Image. This will display the ortho image we just generated in full resolution. Now that we've created an ortho photo, a digital surface model, DSM, and a digital terrain model, DTM, it's time to learn how to export these models, whether you need to send them to a client, share them with an engineer, or import them into another software for further analysis. Let's now click on the Workflow tab and then select Export. This will open the export options where you can choose the type of data you want to export. In the filter bar, type Ortho, and from the list of options, select Color Orthographic Projection. I recommend creating a new folder for your exports and saving each file in its own dedicated subfolder. This helps keep your project organized, especially when you're exporting multiple datasets like the ortho photo, DTM, and DSM. However, you can organize your files in whatever way works best for your workflow. The key is maintaining a clear structure so you can easily locate and share specific exports later on. In the Save as Type field, click the drop-down arrow to view all the available export formats. Here, you'll find several options for how you want to save your ortho photo. If you're working with mapping or engineering projects, GeoTIFF is the best option for ortho photos, DSM, and DTM, because it stores coordinate system, map projection, and geo-referenced corner coordinates. It can be opened directly in GIS, AutoCAD, and software, like QGIS, ArcGIS, Global Mapper. For general visualization or client previews, JPEG or PNG works perfectly and keeps file sizes smaller if they don't need it geo-referenced. Other very useful formats are KML and KMZ. You may be asking yourself, what are KML and KMZ files used for? KML, or Keyhole Markup Language, and KMZ, it's just a compressed version, are file formats used to display geographic data in Earth-based visualization tools such as Google Earth, Google Maps, and other mapping platforms that support 3D coordinates. These files are designed to represent spatial information and are commonly used to share or visualize geographic locations, routes, and 3D models in an accessible format that doesn't require advanced GIS software. Let's examine the KML file format and how to use it effectively with Google Earth. Select KML, then click Save. The Ortho Projection Export Settings window will appear. Ensure that Export World File is set to Yes, and the World File Coordinate System is set to Global. Set Export Projection Parameters to Yes, and change the tile image file format to PNG. Next, choose your desired tile image resolution. For this project, I'll keep it set to 1024 by 1024. Then, click OK to export all the tiles along with the KML file. For this illustration, I'm using a KML file just to demonstrate the concept. However, if you're sharing your project with a client, it's best to export it as a KMZ file instead. A KMZ is essentially a compressed zip file that contains all the necessary tiles, textures, and reference data in one single package. This makes sharing much easier. You can simply send the KMZ file via email or any file sharing service, and your client can open it directly in Google Earth or Google Maps without worrying about missing files or broken references. Go ahead and open the folder where you exported your KML file, and make sure that all the tiles and the KML file are located together, just like I've done here. Keeping everything in the same folder ensures that the KML file can properly reference all the image tiles and data it needs to display correctly when opened in Google Earth. Let's go ahead and minimize this folder and save our project. Click the RealityScan icon and click Save. It's always a good idea to save frequently, especially after major steps like exports or classifications. Even though I already have Google Earth Pro installed on my computer, I've provided a download link in the video description so you can easily install it yourself. It's completely free and available for both Windows and Mac OS. Having Google Earth Pro installed will allow us to open the KML file we just exported and create a virtual tour video where we can visualize our project area in a real-world environment. After you've downloaded and installed Google Earth Pro, go ahead and open the application. When you first open Google Earth Pro, you'll be greeted by the Startup Tips window. You can simply close that. Next, navigate to the top menu, click File, and then select Open. Locate the folder where you saved your KML file and double-click it to open. Google Earth Pro will automatically zoom in and navigate to the exact location where you captured your drone images, allowing you to see your project perfectly aligned with real-world satellite imagery. You'll notice that your KML file appears on the left panel under Temporary Places. The reason it's listed as temporary is because it hasn't been saved within Google Earth Pro yet. For now, it's just loaded for this session, meaning if you close Google Earth without saving, it will be removed. Later, we'll go over how to properly save it so it becomes a permanent part of your project inside Google Earth Pro. Here, you can uncheck the box next to your 2D map layer to temporarily hide the layer you created in RealityScan. If you check the box again, the layer will reload and display your ortho map directly on top of the satellite imagery in Google Earth Pro. This gives you full control to toggle the layer on and off, making it easy to compare your generated map with the actual aerial imagery beneath it. On the top left, Google Earth Pro offers several useful tools that allow you to draw directly on your layer, such as polygons, lines, and paths. You can use these to outline specific areas, highlight features, or label important zones, making your 2D map more visually appealing and informative for your client. Once you finish customizing or adding these details, you can save the modified project and easily send the file to your client, giving them an interactive map they can explore in Google Earth. Let me know in the comments if you'd like me to create a beginner tutorial on how to use all these drawing tools and features within Google Earth Pro. It's completely free software, and I'd be happy to show you step-by-step how to add polygons, paths, labels, and more to make your layers stand out and look even more professional for your clients. Okay, let's create our first video animation using Google Earth Pro. The first thing we're going to do is to drop a place marker. This place marker tells Google Earth the exact location and zoom level where we want the animation to stop. It's an important step because this place marker defines your frame position, and once it's placed, Google Earth will automatically zoom into that place marker during the animation, creating a smooth and cinematic transition. Now that I'm happy with my frame where I want Google Earth Pro to stop, let's click the yellow place marker icon on the toolbar. This will drop a place mark in the center of your screen. You can drag it around to adjust the position. Keep the place marker window open on the left side until you finish placing it exactly where you want. Now that you're happy with your placement, give your place mark a name. You can also change the icon to something more appealing or that better represents your location. Once you're done, simply click OK and then click OK again to save your place mark. If you look at the left panel now, you'll see your new green place mark. Next, zoom all the way out using your mouse scroll wheel until you can see the entire Earth globe. Find the position where you'd like your animation to begin. Once you're ready, double-click the place mark in the left panel to test how the animation looks. That animation looks incredible. Now that I'm happy with how it turned out, it's time to record the video. To do this, first zoom out again and position the Earth globe exactly where you want the animation to start. Then, click the video camera icon located in the toolbar. This will place a recording icon in the bottom left corner of your screen. Simply click Record, then double-click the place mark on your left panel to start recording the animation. Just let the animation play all the way through. Once it's finished, click Stop Recording to end your capture. Google Earth will play the animation again. Please note that this preview animation is only temporary. We haven't rendered the actual video tour yet. That's what we're going to do next. Click the Save button. This will open the Google Earth New Tour window, where you can give your tour a name, and then click OK. You'll now see the saved video tour appear in your left panel. Next, make sure to close the preview playback. If it remains open, you won't be able to render the final video. Now that the preview playback is closed, click on Tools in the top menu and select Movie Maker. In the Movie Maker window, make sure Google Earth has selected your saved virtual tour. If it hasn't, you can choose it manually. Next, select the location where you'd like to save your video file. Choose your desired video resolution, then select the file type and picture quality of your choice. Once you're satisfied with your settings, click Create Movie, and Google Earth will begin rendering your final video tour. Now that the video tour has been created, open the folder where you saved it and play it back to see your final rendered animation. This is a great video you can share with your clients. Use your creativity to add sound effects, background music, or even combine multiple virtual tours to make it more dynamic. The best part is, it's completely free to create using Google Earth Pro. Now is a good time to save all your work. Simply click File, Save, and save your places. You can now exit Google Earth. If you're prompted to save your work before closing, just click Yes to make sure everything is saved properly. Now that you know how to create virtual tours from your 2D drone maps, let's jump back into Reality Capture to export additional file formats and generate professional reports. This time we'll save the ortho photo as a TIFF file instead of a KML or KMZ. Select Color Orthographic Projection, then choose the TIFF file format. Set your desired folder location and give your file a name. After you're happy with your file location, click Save. In the Save Ortho Photo window, double-check that your settings are correct. Make sure Export World File is set to Yes, the World File Coordinate System is set to Global, and Export Projection Parameters file is also set to Yes. Once everything looks good, click OK to export your ortho photo as a TIFF file. Locate the folder where you exported your TIFF file and open it. This looks incredible. This is a high-resolution ortho photo with amazing detail that you can send to your client. They'll be able to zoom in and clearly see every detail captured in the field. Next, let's export the textured model in OBJ format. Select your cleaned model in the 1DS panel and switch your 2D view to 3D view. Make sure you are in the Workflow tab, and then click Export. Search for the OBJ option. This format will allow you to preserve the detailed textures of your 2D model for use in other applications or for sharing with your clients. Select the location where you want to save your file, then click Save. In the Export Model window, expand the Export Transformation Settings section and change the coordinate system to Project Output. Once everything is set, click OK to export your textured model. Next, let's export our point cloud. Click on Export and search for LAS. From the list of options, select LAS Point Cloud. Pick the folder where you want to save the point cloud, then click Save. In the Export Model window, expand the Export Transformation Settings section and change the coordinate system to Project Output. Once that's set, click OK to complete the export process. Next, we'll export the Digital Surface Model, DSM. To do this, select your ortho projection in the 1DS left panel, then click Export. In the filter bar, type Ortho and select Digital Surface Model. Choose the location where you'd like to save the file. Please note that if you want to include elevation data in your digital surface model, you must export it as a TIFF file. The exported TIFF will appear as a black image. This is normal, as it needs to be imported into software such as QGIS to properly visualize and analyze elevation data. If you only need a simple visual export, for example to send as an image or use for presentation purposes, you can export it as a PNG file instead. The same applies to the DTM file. In the Digital Surface Model Export window, double-check that your settings match the ones shown here, then click OK to export your DSM as a PNG file. Next, let's export the Digital Terrain Model, DTM. Click Export. In the filter search bar, type Ortho and select Digital Terrain Model. Choose your desired folder location. If you plan to use the elevation model data, make sure to export it as a TIFF file. However, for this example, we'll export it as a PNG file. In the export window, keep all default settings and click OK to complete the export. Now that you've learned how to export all your models, let's move on to exporting the most commonly requested reports. To do this, ensure that you're in the Workflow tab, then click Reports. Select the Georeferencing Accuracy Report. This report provides detailed information about your camera positions, camera calibrations, and other related georeferencing data. Next, click Report again and export the Ortho Projection Report. This report contains detailed information about your 2D orthophoto, digital surface model, DSM, and digital terrain model, DTM, along with high-resolution reference images. The final report is the Map View Report. Click Reports and select Map View Report. Select where you want to save the file and click Save. This report displays the complete ortho projection along with all its layers, overlaid on a map or satellite image. It allows you to view camera positions, DSM layer, and the DTM layer. Additionally, you can create annotations using the tools provided here, where you can drop pins or make any shapes, lines, or annotations that seem proper for your clients. While RealityScan offers a variety of report options, I've demonstrated the ones most relevant to surveyors and clients. You can also customize existing reports or create your own by exploring the Help section and searching for Reports and Custom Report Template. Congratulations on completing this drone mapping photogrammetry tutorial for beginners using RealityScan and the DJI Mini 5 Pro. If this video gets plenty of views and likes, I will continue to make more beginner videos like this one. If this video helped you or taught you something new, please consider subscribing, leaving a like, and sharing your thoughts in the comments below. Your support helps the channel grow and enables me to keep producing more helpful tutorials like this one. Thank you all for watching, and I'll see you in the next video.